Next up is the ideal gas law. Make sure you're taking notes on all of this, and when I do the examples for all these, make sure you follow along and write that down in your packet. Ideal gases are perfect gases. They're those that fit the kinetic molecular theory perfectly at all temperatures and all pressures. All gases, though, are real gases, where they only fit the kinetic molecular theory at high temperatures and low pressures. We are going to focus our study on ideal gases, where real gases do act like them some of the time. So in doing this, we're assuming that our gases we're dealing with, their molecules are so small that their volume is negligible. We're assuming that their gas molecules are not attracted to each other. And so in doing this, we're going to be able to use an equation for the ideal gas law. And in this equation, you're going to be able to find all the other equations that we will do throughout these videos. So this is the only one you'll have to memorize, and then you'll be able to use all the other ones based off of that. So this equation has to do with 4 measurements you can take of gas. The measurements are pressure, volume, temperature, and moles. And they are related by one constant. So they are all related to R, which is called the universal gas constant. So it stays the same. You will have to know these numbers, and it has 4 units. R equals 8.314 kilopascals times liters over moles times Kelvin. It also equals, there are different numbers for R if you have different pressures. 62.4 millimeters of mercury. So if you are dealing with pressure in millimeters of mercury, this is the R value you would use. Oops, forgot the L. Divided by moles of Kelvin. And the third R is if you're dealing with pressure in atmospheres, is 0.08206 atmospheres times liters over moles times Kelvin. So just looking at the units, you can almost figure out the equation. You're looking at a pressure unit times a volume unit divided by moles and divided by temperature. So R equals, the equation-wise would be the pressure times the volume divided by the moles, which is N, and the temperature. An easier way to deal with this equation would be, though, if you did not have anything divided. So typically, it is written by multiplying by N and T on both sides, so that you have P times V equals N R T. Written like that, many chemists call this Pivnert, the ideal gas law. The only thing to be careful of in using this equation is units. Volume must be in liters. Pressure can be any of the units given. So pressure can be millimeters of mercury, it may be atmospheres, or it can be kilopascals. N is moles, and temperature must be in Kelvin. And R will be the constant based on the pressure units. So let's try an example problem. In your packet, go to number 26. Number 26 says, calculate the volume of 0.0250 moles of nitrogen at 35.0 degrees Celsius and 780 millimeters of mercury. Why don't you first take a moment, pause the video, and write out the givens for this problem. You are given moles. You are given a temperature. And you are given a pressure in millimeters of mercury. And we are trying to calculate the volume. Because our pressure is in millimeters of mercury, our R value will be 62.4. Before we can go to our equation and solve for volume, we need to make sure all of our units are correct. Moles is correct for N. Temperature cannot be in Celsius. We need to convert it to Kelvin. Kelvin is always higher, so we are going to add 273. So our temperature is 308 Kelvin. Pressure can be in millimeters of mercury, and we have our R. So we write out our equation. P times V equals nRT. Solving for V, I'm going to divide both sides by P. I like to do my algebra without the numbers. It is less writing. You are less likely to make a mistake. So the volume will equal the moles times the R value times the temperature, all divided by the pressure. So 0.0250 moles times 62.4 millimeters of mercury times liters over moles times Kelvin times 308 Kelvin. And it really should be 308.0 Kelvin, because we could say the 273 is exact. We should keep that sig dig, that 0.0 after it. And this is all divided by the pressure of 780 millimeters of mercury. You can see that unit-wise, moles divided by the moles in the R will divide out. Kelvin will divide out, and millimeters of mercury will divide out. This is how you know you're on the right track. The only unit that didn't cancel was your volume. Take a moment and make sure you get the right answer. Plug this into your calculator. The answer with correct significant digits, since they all have 3, and you should not be using R for its exact, is 0.616 liters.